Hello, welcome everybody. Welcome to this presentation. Today we are going to solve a problem on wedges. So we all know solving the problem on wedges, we apply the concept of sliding friction. So wedge, it is nothing but a simple machine which we commonly use to transform an applied force into a much larger force. Or it is used to give a small displacement to adjust some heavy loads or for positioning some heavy loads. So one such problem we will see today. So the problem is to determine the force P to move the wedge downwards, and the angle of friction is 15 degree for all the surfaces. So this is the given surface. We have one horizontal surface and one inclined surface. So the inclined surface is inclined to an angle of 75 degree with the horizontal. So the two surfaces are given, a block is given. So this block is 100 kilonewton self weight, and a 2.5 kilonewton load is applied from the right towards the left. So another wedge is given. So this wedge is a machine. We have to apply a small load in order to move this block so that this wedge will be moved downwards. So we are asked to find how much force P you have to apply so that you can move the wedge downwards. So the angle of friction is given as 15 degree. So from that we know the coefficient of friction. Normally we symbolize it as mu. So that is equal to mu is equal to tan 15. So the value for tan 15 is 0.2679. So you can see the angle of friction 15 from the diagram. So this is your given problem. Two surfaces, one horizontal surface, one inclined surface, a block of load 100 kilonewton. A load of 2.5 kilonewton is applied on the block. A wedge is positioned between the block and the inclined plane. We are required to find the force P required to move the wedge downwards. So for solving this problem, we have to draw the free body diagram. So we have two objects, two bodies. One is the block and another is the wedge. So first of all, we will draw the free body diagram of the block. So our block is 100 kilonewton self weight and 2.5 kilonewton is acting from the right. So these are the given things. Now this block is resting on the horizontal surface. So when it rests on the horizontal surface, there is a contact between the surface and the block. So there will be a normal reaction acting perpendicular to the surface. So this normal reaction is taken as R1. So this acts normal, perpendicular to the surface. So you can see there, that is R1. Now the frictional force. So R1 is the normal force. So when there is a movement, a frictional force acts perpendicular to the normal force. So when you are moving the wedge downwards, your block will be tended to move towards the right, so that our frictional force acts in the opposite direction. Frictional force acts towards the left. Now there is another contact between the block and the wedge. So the force acting normal to this contact surface is taken as R2, and we know that the wedge is moved downwards. So when the wedge is moved downwards, the moment experienced by the wedge will be downward moment, and the moment experienced by the block will be an upward moment, so that the frictional force experienced by the block will be opposite to the movement of the block. So the frictional force experienced by the block will be in the downward direction, that is F2. So we take the normal force between the wedge and the block as R2, and the frictional force between the wedge and the block as F2, that is equal to mu into R2. So next we will see, we have to draw the free body diagram of the wedge. So this is the wedge and applied load. P is the applied load which we have to find. So there are two contact surfaces for the wedge. One is the block and the another one is the inclined surface. So while considering the block, contact surface on the block, contact on the block, the normal force, the normal reaction force acts leftwards. So that is taken as R2. So naturally the frictional force will act in a perpendicular direction to that of R2. It will act normal to R2. So wedge is moving in the downward direction. So automatically our frictional force for the wedge between the block and the wedge will be in the opposite direction of the movement, that is in the upward direction. So it is shown as F3. So F3 is equal to mu into R3. And we have another surface of contact, that is on the inclined surface. So for this inclined surface, the normal reaction acts perpendicular to the inclined surface. So that is taken as R3. R3 acts at a 90 degree to the surface. So it makes an angle of 15 degree with the horizontal with respect to the surface. So this is how this makes an angle of 15 degree with the surface. That is the reactive force, the reactive normal force R3 makes an angle of 15 degree with the surface, because the inclined surface is making an angle of 75 degree with the horizontal. So our force, normal force about the surface will be 15 degree to the horizontal. So now the wedge is moving downwards, so automatically there will be a frictional force acting in the opposite direction, normal to the normal reactive force. So that is taken as F3, that is equal to mu into R3. So these are the two free body diagrams, free body diagram of the block and free body diagram of the wedge. And we have the value for coefficient of friction mu is equal to 0.2679. Now for solving this problem, we have to resolve the forces using the equilibrium conditions. We know the equilibrium conditions are summation of the horizontal forces is equal to 0 and summation of the vertical forces is equal to 0. That is sigma fx is equal to 0 and sigma fy is equal to 0. So resolving these forces, first of all, see we have four unknowns, R1, R2, R1 and F1. So F1 is written in terms of R1, mu is known. R2 and F2, F2 is written in terms of R2. R3 and F3, F3 is written in terms of R3. So the unknowns are R1, R2, R3. And another unknown is the external force that has to be applied to the wedge in order to move the wedge downwards. So totally we have four unknowns. So from the free body diagram, we have two free body diagrams, free body diagram of the block and free body diagram of the wedge. So free body diagram, from the free body diagram of the block, we will have two equilibrium equations, sigma fx is equal to 0, sigma fy is equal to 0. And from the free body diagram of the wedge, we have two equilibrium conditions. So sigma fx is equal to 0, sigma fy is equal to 0. So totally we have 4 unknowns, 4 equilibrium equations. So using these 4 equilibrium equations, you solve these 4 equilibrium equations, we will be getting the value for P. So next our aim is resolving these forces. So first of all, we will resolve the forces for the block. So for the block, we take the equilibrium condition. So sigma fx is equal to 0 and sigma fy is equal to 0. So when you take sigma fx is equal to 0, we get R2 is equal to 2.5 plus mu R1. That is, summation of all the horizontal forces is equal to 0. When we take sigma fy is equal to 0, we get R1 is equal to mu R2 plus 100. So now we will consider the free body diagram of the wedge. So while considering the free body diagram of the wedge, the forces R2 and F2 are horizontal and vertical, but the normal force R3 is an inclined force. Similarly, F3, that is frictional force, F3 is also an inclined force. So when these are inclined forces, we have to resolve it into horizontal and vertical forces. So now we can see we have how to resolve the forces. So the forces are marked with respect to the horizontal and vertical axis. So these forces are resolved into horizontal and vertical components. So now these are the equations of the wedges, equilibrium equations from the free body diagram of the wedge after resolving it into horizontal and vertical components. So we get sigma fx is equal to 0. So R2 plus mu R3 cos 75 is equal to R3 cos 15 and mu R2 plus R3 sin 15 plus mu R3 sin 75 is equal to P. So now totally we have 4 equations from the 2 free body diagrams. So the first 2 equations are from the free body diagram of the block and the third and fourth equations are the free body diagram of the wedge. So we have 4 equations and 4 unknowns. Solving these 4 equations, we get the values for R1, R2, R3 and P. So the total force required to move the wedge downwards is 26.605 kilonewton. Thank you.